Okay, so hello everyone, thanks for coming and thanks for having me here. Today I want to share some experience about building LLVM based tools. Yeah, just a few words about myself. So my name is Alex, I work at a company called PT Scientist GmbH. You can find me on the internet if you want to, like my blog or Twitter. So yeah, this is the agenda for today's talk. So basically, these are just like set of some somehow like random but general enough tips and tricks that might be helpful if you want to build something based on LLVM. So the tool I'm talking about is called MAL. I built it with some friends and colleagues like for several years, like 3 years something. The source code is available on GitHub. If you want to know more about the tool itself, then I encourage you to watch my talk from FOSDEM 2 years ago. Yeah, besides that, I'm not going to talk about the tool. So everything will be kind of general. So a few interesting things, in my opinion, that the tool works on Linux, FreeBSD, and macOS. It may work on Windows, but just no one has access to Windows machines. So. And the nice part also that it can be compiled against any LLVM version between in between of 3.9 and 7. Yeah, and another interesting part, in my opinion, is I think it has it provides quite nice user experience. So here I have just a normal program. Yeah, it runs like some tests in this case. But then I can also do the following. Oops, sorry. Yeah, I just run my tool against that binary, and it works. And it operates on the bitcode level. So I find it quite nice comparing to some other tools that I've seen. But let's get back to the slides and begin. So just to have some framework in mind, I defined LLVM-based tool as something that operates on LLVM bitcode, and it does the following things. It parses or loads the bitcode files in memory, like creating LLVM modules. Then it does some analysis, and then some transformation potentially, and in the end it does some like processing. So the tool can be something like a compiler or obfuscator, or like in our case, tool for mutation testing. So I think this approach is general enough. Of course, there might be examples where it doesn't fit, but I just want to have some kind of structure. So the first thing that you should consider, of course, is the build system. And I think lots of articles and documentation suggest to use LLVM config. It may work if you just start something fast or like some prototype, but in the long run, it's not really good. And there are a few quirks still. So this is how usually looks like. So you just use Clang, then you call LLVM config, you ask for C++ flags and linker flags and so on. So the first problem, the C++ flags. So these are likely not the flags you want, but these are the flags that LLVM was compiled with. So here, the first one, just some part of it, it's just an example. Include years, valid, you need it, obviously, but for example, this -w error, I think it won't compile with GCC because it's some Clang-specific thing, and it may also not compile with older versions of Clang. So yeah, another point that unless you compile LLVM yourself, you will likely get optimized version. So if you build your tool using this C++ flags, then it will be compiled in optimized way all the time. So yeah, you should just be aware of that. Another thing that the LLVM config for libraries and linker flags, it works really good, really well, but there are some other issue. If, let's say, you have on your machine installed more than one version of LLVM and you have lib LLVM dilib, then eventually you may get this problem. So if you compile against, if you link against some library, specific library like LLVM support, for example, and you run, you may get into this inconsistency, blah, blah, blah. I don't really understand where it comes from. There something goes wrong, obviously, with dynamic linking and maybe static linking as well. But the solution for that problem is to actually link against just lib LLVM. The kind of issue of LLVM config that there is not really an easy way to check whether you have the sleep LLVM installed or you don't have it. So yeah. As a solution, I do consider CMake. If you don't know well, you probably know what CMake is, but if you don't know how it works and what it does, I encourage you to just read this documentation. It's good enough introduction, and from now on, I assume that you understand CMake. If not, please do yourself a favor, read about it, and then you can get back to slides, and yeah, it may make sense afterwards. So how to use LLVM with CMake? Yeah, that's straightforward. So you just use the find package, and you search for LLVM. When it's done, you get access to all the variables that LLVM distribution provides to you, and also the libraries. So important part here, you may see in kind of reddish color search paths. They are specified in this way. The reason, because as we tend to support many different versions of Clang and LLVM, different versions on different distributions of Linux and Mac, they have different locations of different places where CMake looks for. So the recommendation is, yeah, to do it this way. Two other parts, pass to LLVM, that must be provided from the outside by your user, by a user of your tool, because if you don't do it explicitly, then there is no guarantee which actually version of LLVM is used, and it's getting a bit tricky. The good part that you can also do it the same with Clang, find a package Clang, but it's broken on some Linux distributions, especially if you have, I think, Ubuntu. If you have 3, 9, 4, and 5 installed at the same time, then it doesn't work because, some prefixes, suffixes with versions. Just in that case, recommendation is to use pre-compiled versions of Clang or LLVM from official website. Yeah, so once you've done that, you get access as I said, to variables like LLVM include years, and you can teach your targets, like where to look for headers, and you can link against LLVM support, for example, as you would link to against any other library in your project. Except that, you may face this problem, and it's really annoying. So the proper solution is to actually check if distribution of LLVM you use, if it supplies this LLVM target, LLVM library, then you link against just LLVM. Otherwise, you link against your libraries any you want. Okay, I think we're done with CMake for now, and getting to, we're not quite done with CMake. So how to support server versions? There are two approaches. This is the one of them. So basically, we have just a bunch of folders. They provide a set of kind of glue code for different versions of LLVM. And then, the header files, they look like this. So basically, all the places that have some incompatibilities between versions, they were hidden behind some functions. And also like type defs used and so on. It's not much here, actually, I must admit, and you probably may face many more discrepancies between versions, but I think it's still manageable and it's a good enough approach. So, in fact, in our case, we also used orgjet, and it was changing a lot between different versions, like a lot. And we first tried to come up with some interface to hide the changes behind, but at the end, we just realized that our use case, that orgjet is too general for us, and the maintaining this part is just harder than actually crafting our own JIT engine, which we did, and it just works so far. I think the other approach is to you use the define, like the macros, if, like in your code base, like sharp if LLVM version less than 5 or something. It's still doable, but it's a bit messy, and I think just as a personal preference, I like this approach more. In the CMake, it looks like this then. The real code is a bit more sophisticated, but it's just an example taken from our CMake file. yeah, just checks if there is kind of glue code for the version, then it picks it up. Otherwise, yeah, error. Yeah, so far I was talking only about case where you compile your tool against precompiled version of LLVM. But it does make sense also to compile against sources for the following reasons. With precompiled version, you have like really fast compile time, but it's really hard to debug because you cannot dive like deep into internals, and you only have interface. So it's hard to put printfs for sake of debugging. And there are no asserts, unless you compile LLVM yourself. And so, for example, we didn't compile with asserts for maybe a year or something, and then we got several bug reports from a person who was adding FreeBSD support. And this person used built with assertions enabled. And we just learned that many times we violated some constraints of LLVM. And if you enable assertions, then it crashes. But it worked in our case somehow, like rather by accident, but still. Yeah, so as a downside of building against source code, you have lots of time to actually build LLVM. So the good part that you can also set up your CMake to support both things at the same time. So either compile against precompiled version or against sources. So the trick is simple. It's probably fragile, but it works. And yeah, I'm glad about that. But so basically you just check if the LLVM folder that a user provides, if it contains CMake-less file, then you just add LLVM itself as a sub-project. So now you own LLVM and not the other way around. The problem here that you don't have things like LLVM include years and you don't know LLVM version, because those files, they are not exposed. Like these variables are not exposed. Again, there are some solutions for that. Another fragile solution. So you can pick any random LLVM library and read its property. For example, include directories. And yeah, that works as well. So as for the version, you can just parse the CMake-less file and use regular expressions to get the version out of it. Then, it just works. Yeah, and I think now we are done with CMake. So now, I want to talk about memory management. I'm not sure. Yeah. Is there any problem here in this code? Anyone knows? Okay. So it may crash or may not. It depends on which version you use. I think 3, 8, and 4 it will crash, and on the recent versions it will work, I think. So the problem is that, or rather, let's start with the solution. You should just switch those 2 lines. The problem here that LLVM context actually owns the modules. So, and it stores just rough pointers, like a vector of rough pointers to all the modules that were created. And in this example, the context deallocates. The LLVM context owns the modules, and in the destructor, it just calls the delete to the actual pointers. So this code, when it executes LLVM context, it destroys, like deallocates the modules, then happens deallocation of the vector with all the modules, and double free. So basically, you get a crash. For the same reason, this example. So this is I think we had this problem before. So assumption was that in the nested scope, you create a module, you do something with it, and it's just like disposed, like deallocated after the scope ends. But we faced a problem on a machine, 32-bit machine with 4 GB of RAM, because actually modules are not deallocated, and they are stored in the LLVM context. So the solution here is to use some local context. Then your memory is freed at the end of the scope. Another kind of annoying part was this approach. All the modules, they are loaded in the global context, and when the program terminates, you just see that like nothing is happening, and that's because LLVM just frees the memory. So in that approach, this work is still done, it's still happening, but it's kind of distributed across the whole program lifecycle. So it's not yeah, the execution time takes the same time, but it's just less annoying or frustrating. Okay, next topic is parallelization. So the trick here to make things parallelizable is to not use LLVM passes. It's a bold statement, but I will elaborate just in a second. So I know like at least two classes in LLVM that are not thread safe and that are heavily used. It's LLVM context, and therefore like anything you do with modules, instructions, functions, it's also not thread safe because it's like tightly coupled with LLVM context. And the same goes for the target machine. So if you use like org compiler, for example, or if you do any code generation, then it's not thread safe. So let's look at the example. Yeah, this tooling is just perfect for fair parallelization because what it means that you have like 10 tasks and you have 10 threads, and you can just evenly split those tasks across threads, and you get you gain some performance. So just as an example, let's say we have 3 bitcode modules. We want to load them into memory, parse, and do some job. So if you want to do that across 2 threads, then each thread should have its own LLVM context. Otherwise, it's not thread safe. And what happens next? If you want to do some analysis, so in this example, we have 6 functions. It may make sense to split all those 6 functions across 2 threads because you just do analysis. You do not do any modifications. And you can actually do that. Yeah, it works. So there is kind of bold line where a function escapes its thread boundaries, and it's fine. But when it comes to transformation, then you cannot do that anymore. So each function should be transformed in the context or in the thread of the same module of the same LLVM context. And these are some numbers. So yeah, you see the steps are split: analysis and transformation. So the transformation, at least in our case, is super fast because, yeah, for some reason it's super fast because it does much less job. But analysis takes like most of the time. And if we parallelize, like you can see the green color, it becomes just much faster. So that's why I'm saying that you maybe should avoid using passes because they kind of incentivize you to put like analysis and transformation into the same thing. So yeah, if you split these steps, then you can parallelize better. But of course, you should measure everything all the time. So this is, yeah, in our example, in our case, just loading, like parsing bitcode files, loading them from disk takes much more time than analysis and transformation. It doesn't matter, like sequential execution in parallel. So yeah, you still can use passes if that's the case for you. But yeah. Getting bitcode. That's, I think, yeah, one of the trickiest topic. One of the kind of selling point of LLVM that it has the bitcode that can be shared across different compilers and so on. That's still the case. But yeah, if you want to build some tooling, there is not really easy way to get this bitcode, depending on the compiler and so on. But there are some ways to do it for Clang at least. Yeah, for other compilers languages, yeah, please talk to developers of those languages. So normally, like compilation flow is like that. You have an object file, so you call a compiler with some flags. You have an object file, then you call a linker, and you get executable in the end. So with Clang, there is at least, yeah, the most famous flag. So if you call Clang emit LLVM, and instead of object file, you get LLVM bitcode, and there is no executable. Another one, LTO. So you can call LTO, like -f LTO, and you get, instead of the object files, well, you still get object files, but they do not contain machine code, but they rather contain LLVM bitcode. And at the end, you have normal executable. So that works pretty well if you have some well-defined build system, like CMake, for example, or even like Makefiles, if you have those intermediate files. But if you just call clang and like 10 source files, then there is no output of bitcode, or no output with object files, then it doesn't work. And the best approach that actually we use, or we adopted recently, the f-embed bitcode. So if you call this code, then at any stage, your either object files or executables, they do contain both machine code and LLVM bitcode. And you can actually extract it easily. So there is a tool called libebc. I think it stands for embedded bitcode. So what it does, it just extracts the bitcode file from an executable. It works both on Linux and Mac and FreeBSD. And the original tool works. It just does extract the files and stores them locally on disk so that you can do some post-processing on them. And so I made a fork to make it work with in memory. So everything happens in memory as I showed at the very beginning. So super straightforward. I will be upstreaming the patches soon, so the original version should get the support if we agree with maintainers. But otherwise, you can check the things out. These are examples how it works. So you just call ebc-util, and then you get a bunch of bitcode files, or you just call the tool. I think the last point, multi-OS support. So we are not that many people working on this project, and it's really tough to maintain these things. So I can just recommend, say 2 words like Vagrant and Ansible, just like the way to go. So what Vagrant does, it's just a system that operates, or that helps you manage virtual machines. It supports VirtualBox, VMware, Docker, I think, anything you can imagine it supports. So in that case, I have just like one file with that many lines that, then I run background up Debian, for example, and I have a virtual machine running ready with everything I need on it, so I can just start debugging right away. I can SSH into it, and then when I'm done, I just can destroy it to dispose the memory. And the good part of it that if you have some IDE that supports remote debugging, so as, for example, CLAN does have it, you can run this, set up this virtual machine, then connect with CLAN, and this is at least, for example, how I work on Mac. I do have native experience as a Mac user, but I'm running and debugging my software on Linux. It's very useful. The second part is Ansible. So here you may notice like VM, provision Ansible, and then a playbook, Ubuntu YAML. So what playbooks are, it's just like set of some tasks that needs to be done. This is an example of things. It's just a YAML file, does something, and so for, in our case, most of the parts, they are shared between all the other operating systems, like FreeBSD, and Linux, but it's slightly different on Mac. But the cool part about it that I can also run the Ansible thing locally. So, for example, if I get a new Mac machine, I just use our macOS tasks to set up things locally. What else? The other benefit of the Ansible scripts or playbooks that you can also use it like on CI and everywhere you want. So at this point, I think that's pretty much it. So I try to come up with things that are general enough to be applicable for everyone. So this is not all the problems or issues we have solved so far, but I hope that it will help you to build better tooling around LLVM. Thank you, and questions. Question?
Thanks for your talk. I found it super useful. To kind of pile on the LLVM config hate, I noticed you were linking against libclang tooling. Did you try to link against any other parts of Clang, not LLVM, but Clang parts, and find any issues with like linkage order?
So the question is if I had any issues with the linkage order when using LLVM config. And yes, I decided not to include it into the slides because that's a mess. But we had this problem. Yeah, with different versions of LLVM and Clang, there were like some problems with different order of things. So we ended up wrapping everything in like start group, end group, linker flags. Yeah. Or on Mac, it was like something like -w, like whole archive or something. So I mean, it's just like super hard to support because you have if macOS, then you have one bunch of scripts, else if Linux, other, and so on and so forth. But with CMake, no problems whatsoever. Just works.
Yeah, it's awesome to see how wide support you have across all these different OSs and,
yeah.
and versions as well. It's really cool stuff. Thanks.
Yeah, thank you. Yeah.
As far as I know, OrgJIT was supposed to improve upon MCJIT, but in the end, you still end up using your own JIT. So what was wrong with it?
Yeah, so the question is that why don't we use OrgJIT or MCJIT and come up with our kind of own solution? So one of the problems that we had with MCJIT initially that it requires you to give up ownership of all the modules. So for all the modules, it's like unique pointer, and you need to give up it, so you don't own them anymore. And in our case, we wanted to own it hardly, so we cannot use MCJIT. Therefore, we switched to OrgJIT because it didn't have this problem initially. But as the time grows, like there was this problem as well, and the API changed drastically. So it was just too much overhead to actually support our own kind of interface to the OrgJIT. So, and we don't need most of the features that it provides, like on-request compilation, and yeah, we just load program at once, and that's it. Yeah. So, thank you, enjoy the day, and yeah, see you around.